Okay, so now that we've discussed vector spaces and their corresponding dual space, we have all the machinery that we need to go on to generalize this concept to tensors. So I'll just remind you what we've constructed so far. We have a vector space, which is just a set on which we have the operations of vector addition and scalar multiplication, as we've defined previously. And this, I'll remind you, is a vector space over the real numbers. So then from this vector space, we constructed its dual space, which we defined as the set of all structure-preserving or linear maps between the vector space and the underlying field. And we saw that because these maps are linear maps, that guarantees us that this other set, this dual vector space, is in fact a vector space in its own right. So elements of this dual space are the dual vectors, which we understand as being linear maps from the vector space into the real numbers. And now I briefly mentioned how, just as we can view the dual space as the set of all linear maps from V into R, we can equally view the vector space as the set of all linear maps from the dual space into R. So a vector is simply just a linear map that takes a dual vector in this slot into the real numbers. So now to motivate tensors, I just want to begin by asking you to consider the following space. V Cartesian product V. So I'll just remind you what this Cartesian product means. This whole thing, V Cartesian product V, is just a set, and the elements of this set are these so-called ordered pairs. So these ordered pairs, one element, the first element, is just a vector from V, and then the second element in the pair is a vector from our second V. And now this thing is ordered in the sense that it matters which slot you write these in, and the ordering of the slots tells us which of the vector spaces the corresponding vectors come from. So we've constructed a new object, the so-called Cartesian product space, which elements consist of these pairs of vectors. Now we want to consider or construct a map from this pair of vectors into a real number. So let's just pause for a second and think about how we might possibly do this. Well, we have two vectors, and we know how to map individual vectors into real numbers. We simply feed them into a dual vector. So we might guess that in order to map this pair of vectors into a real number, we're somehow going to need a pair of linear maps. And that's exactly what we are now going to construct. So I'm going to construct now a tensor, which I'm going to call T. And this tensor is going to be formed out of two dual vectors taken together using a new symbol, which is called the tensor product. So this whole object, this T, now is the map which maps this pair of vectors into a real number. And the way we understand this map as acting, if I just briefly use the function E notation, we feed the two vectors into our tensor object, which then acts in the following way. So we know that this is just a real number, this is just some other real number, and then they're multiplied together using this tensor product, which on real numbers just reduces to regular multiplication. So this whole thing is just a real number. So we've succeeded in mapping this pair of vectors now using this pair of linear maps strung together using this tensor product. We've mapped the input, which is two vectors, into a real number. So we can further understand this using our bracket notation as simply being we feed the first vector into the first dual vector, which is then taken in a product with the second dual vector and the second vector. So now this new object that we've constructed, this T, which it might help to just put brackets around So we know that this is really just one object by itself. This T is what we call a multilinear map. What does this mean? Well, it simply means that the map has to be linear in each of its slots. So we know that individually these maps are linear. To be a multilinear map, we must have that if we feed into the tensor an object which looks like a sum, so now the first vector that we're feeding it is itself a sum of two vectors. I could make it absolutely clear. To be a multilinear map, we require that this, and this would work the same if we had in this slot another sum of vectors. So we'll have more to say about this multilinearity in a second, but for now I just want to continue exploring what this T object is and what it looks like. So we know that for our vector space and its dual, we have a basis where we defined the basis vectors according to the following rule. So we have epsilon, I'm going to use Greek indices, epsilon mu being the dual basis, and then the vector basis. We defined them through the rule that when you map the basis vectors, this is just equal to the Kronecker delta. So now if we consider this tensor object, and we consider expanding all of these objects in terms of a basis, we get the following result. So here I've just expanded each of these vectors and dual vectors using the corresponding dual and vector basis. So these are the scalar components of each vector and dual vector. Now we know because this map has to be multilinear, we can just pull all the scalars out as we would expect. And now we're left with something which we know how to compute entirely, since we have defined how the basis vectors map using this rule. So this just simply gives, which then simply reduces to, and now because these are just all simply scalars, and we know the sum convention, this just overall gives a real number. We have a real number multiplied by another real number. So this is how we compute the map in practice using this rule. We simply expand out our vectors that we're feeding into the tensor in some particular basis, and then we go through the calculation and we arrive at a fairly simple result. And the key property that allowed us to do this expansion is this multilinearity, in that we can pull these scalars out and just treat the basis vector maps on their own. So now one last thing before we generalize this even further. We think of the tensor as being this tensor product of two dual vectors. So we know now how this should act. It should be a map which is simply waiting for two vector inputs. But now if we come back over here, we can expand each of these in terms of a basis, which gives us the following result. And now we remember this is multilinear, so we can write this as omega mu sigma nu. Then we have just the basis vectors themselves in a tensor product. So now this is a nice expression because we've separated out effectively the vector part and the components part. So you'll often see this now written as simply T mu nu with two indices, which effectively stands for both of these components. And then we have that the tensor has its basis as follows. So now we understand this as just being maps that we can then feed into any vector, and using the multilinearity we can pull the scalars out. So we often just ignore the basis vectors completely, and we just talk about the tensor in terms of these components. So you'll often see tensors written, particularly in physics, just referring to their components, and the basis is left implied or understood. Whilst this makes all of our expressions cleaner and easier to handle, it really hides the guts of what's actually going on with this tensor object.